Okay, so 3.7a is really just asking you to prove what we claimed at the very end of 3.3.1, which is sort of the whole thing leading up to the Gram-Schmidt orthogonalization procedure. So suppose that you have two eigenfunctions of the same operator q hat with the same eigenvalue little q. So in that case, I have q hat times f of x is giving me the eigenvalue little q multiplied by f of x, and then I have a degenerate eigenfunction g of x, which I'm going to write as q hat acting on g of x is equal to the same little q times g of x. And I'm basically trying to prove that any linear combination of f of x and g of x is also going to be a degenerate wave function with the exact same eigenvalue little q. So obviously the first thing we start with is just to write out a linear combination of f and x, of f and g. So c1 times f of x plus c2 times g of x. And at this point, what I'm trying to do is I'm trying to show that I can operate on this with q hat, and it's going to give me the exact same sort of expression as I have up here, where this ends up becoming an eigenfunction of q hat with the same eigenvalue, little q, on c1 f of x plus c2 g of x. And this is really just kind of a trivial proof because, obviously q hat just distributes into f and g, which means that you have c1 q hat acting on f plus c2 q hat acting on g, which is equal to c1 q f plus c2 q g, which is then equal to, just via distributive property but in the opposite direction, g times c1 f plus c2 g. Therefore, you've proven this, this entire statement, and you're done with part A. Okay, I've thought about this over a little bit, and I realize there is one sort of slight logic gap here. And honestly, most people that are just doing this problem probably won't notice this, but if you're especially observant, you might realize that this sort of statement that I've defined here isn't necessarily always true. It sort of relies on the assumption that q hat is linear. And in general, yes, it is linear. That is a correct assumption. However, you might be tempted to ask, well, what about in the hypothetical scenario where you have an operator that isn't linear? And my response to that is you don't have to worry about it. Realize that quantum mechanics sort of works in the language of linear algebra. Linear is in the name. And in general, as long as you're dealing with sort of finite matrices, aka as long as you're dealing with operators in a finite dimensional space, which we always will be working with, because, we have a finite number of spatial dimensions, your operators that correspond to those respective matrices will always be linear. So because of that, you can always just assume that your operator is linear. Taking the alternate hypothetical of having nonlinear operators starts sort of going deeper into parts of QM that are a lot more fringe and sort of not really the focus of a beginner level introductory course like this. Okay, part B is a two-parter. First off, we want to show that these two functions, exponential of x and exponential of negative x, are eigenfunctions of the second derivative with the same eigenvalue. So let's do that first. Apply this operator, which is d2 by dx squared, onto each of these functions. So first off, e to the power of x. This is going to give me d by dx of e to the x, which is equal to e to the x, which is equal to the value 1 times e to the x. Therefore, your eigenvalue is equal to 1. Same thing, second derivative, this time e to the negative x. This is going to give me d by dx of negative 1 e to the negative x, or positive 1 e to the negative x. Therefore, over here, same thing, the eigenvalue is also positive 1. Next, we wish to, construct two linear combinations of f and g that are orthogonal eigenfunctions on the interval from -1 to 1. So first off, it wants us to make two linear combinations of f and g. So let's just define an arbitrary linear combination of f and g. So that's going to be c1 times e to the x plus c2 e to the negative x. Now, what's the simplest choices you can choose for c1 and c2? right? The simplest is 1, 1, and then 1, negative 1. Or the other way around, negative 1, 1, however you want. So I have e to the x plus e to the negative x as my first linear combination, and I have e to the x minus e to the negative x as the second linear combination. So then what I want to do now is I want to prove that these two functions are orthogonal on the interval from -1 to 1. And if you know a little bit about linear algebra already, then you can do this without even hard proving it with an integral, because it's very obvious, if you look at this head on, that these two functions are linearly independent. You know, there's no scalar you can multiply one function by to get the other. And by definition, linearly independent functions will integrate against each other in an inner product to always equal 0. Now, if you don't know this, you can prove it, the hard way through an actual integral, in which case, well, the inner product of, let's call this one big F, and let's call this one big G, right? The inner product of big F with big G is going to give you, remember our interval is from -1 to 1, e to the x plus e to the negative x multiplied by e to the x minus e to the negative x. If I then multiply this out, let's see, e to the x squared minus e to the x e to the negative x plus e to the negative x e to the x minus e to the negative x squared. This first term is going to give me e to the 2x minus 1 plus 1, because these two are just, inverses of each other, minus e to the negative 2x. The 1's cancel out, leaving e to the 2x minus e to the negative 2x dx. Integrating this, 1/2 at the front, same thing, minus -1/2, so plus 1/2 e to the negative 2x, from -1 to 1. 1/2 e squared plus 1/2 e negative squared minus 1/2 e negative squared plus 1/2 e squared, in which case, let's see, this term cancels with this term cancels with this term, therefore we have 0, therefore the integral is 0, therefore our, our two sets of linear combinations are orthogonal because their inner products integrate to 0.